Welcome back. Here's a potential 3n+1 circuit of length k with x up moves and k minus x down moves. The member of this loop at the bottom will be 3 to the x minus 2 to the x over 2 to the k minus 3 to the x. And we're trying to see if this is an integer. For example, in this loop, the numerator 19 is not evenly divided by 5, so this loop will be full of fractional numbers starting with 19 over 5 at the bottom. We're trying to show that no matter what x and k you pick, 3 to the x minus 2 to the x will never be divisible by this denominator. And when x and k get really big, it's hard to tell if this divides evenly. That's why we're interested in how things factorize. If we know something about the factors, then maybe we say whether there's an even division or not. In this episode, let's take a step back and look at some simpler denominators. For example, 2. Does 2 ever divide 3 to the x minus 2 to the x? No, it never does, because this numerator is always odd and only even numbers are divisible by 2. How about 3? Nah, 3 to the x minus 2 to the x is never divisible by 3. There should be an English word for divisible by 3. Just like 2, 4, 6, 8 are even numbers, 3, 6, 9, and 12 are threeven numbers. Some people say threeven or trisectable or 0 mod 3. I guess when they invented English there were some oversights. Anyway, 3 to the x is divisible by 3, but 2 to the x never is. 2 is 2 mod 3, 4 is 1 mod 3, 8 is 2 mod 3, and so on. There's no 0 mod 3 in this cycle. How about 5? That's a different story. 5 divides 3 to the x minus 2 to the x all the time. Well, not all the time, but whenever x is even. And how about 7, 11, 13? Each one divides 3 to the x minus 2 to the x an infinite number of times. For example, 7 divides it whenever x is a multiple of 6. How about a composite number like 19 times 211? Well, 19 divides it every third x, and 211 divides it every fifth x, so 19 times 211 divides it every 15th x, because 15 is the least common multiple of 3 and 5. Even a million billion is going to divide 3 to the x minus 2 to the x periodically with some regular period. Okay, let's try something harder. Is 3 to the x minus 2 to the x ever divisible by 2 to the k minus 3 to the x for any x and k? That's too hard. How about is 3 to the x minus 2 to the x ever divisible by just x? For example, is 3 to the 5th minus 2 to the 5th divisible by 5? Let's see. 243 minus 32 equals 211. Nope, not divisible by 5. How about 3 to the 100th minus 2 to the 100th? Is it divisible by 100? Or 3 to the million and 3 minus 2 to the million and 3. Is it divisible by a million and 3? So let's divide and conquer. So first, the case where x is prime. Is 3 to the x minus 2 to the x divisible by x? Remember, when we look at the 2 to the x mod some prime p like 5, the remainders cycle like this, 2, 4, 3, 1, 2, 4, 3, 1. There's always a 1 here at p minus 1. That's Fermat's little theorem. So if we look at 3 to the 5th mod 5, where the red star is, it's going to be 1 times 3, or 3. And 2 to the x is 2. So 3 to the x minus 2 to the x is 3 minus 2, or 1. And same thing for 3 to the 7th minus 2 to the 7th, mod 7, or 3 to the 11th minus 2 to the 11th, mod 11, and so on. That means 3 to the x minus 2 to the x is never evenly divided by x when x is prime. There's always a remainder of 1. So without too much calculation, we can say a million and 3 doesn't divide 3 to the million and 3 minus 2 to the million and 3. All right, how about the case where x is composite? Say it's the product of two primes like 5 and 7. We can't use the same trick because 3 to the 34th and 2 to the 34th aren't 1 anymore. Fermat's little theorem doesn't apply when x isn't prime. But 35 divides 3 to the x minus 2 to the x exactly every sixth x, because 6 is the least common multiple of the periods of 5 and 7. And multiple here means that this period 6 is a composite number. But to hit 35, we'd need the period to be every fifth x or every seventh x, which are primes. So it's going to miss. And that means 3 to the 35th doesn't equal 2 to the 35th mod 35. There's some edge cases to consider, like if p and q have the same period, but let's not worry about it. Okay, pretty cool. So 3 to the x minus 2 to the x is never evenly divided by x. So how about the tougher problem? Well, stay tuned for the next episode.